Okay, we've looked at area problems. Now let's look at volume problems using calculus. And keyword here, which I'm going to write on here, is cross sections. So this is the first type of volume problem we're going to look at when you're dealing with the cross section of an object. And let's go ahead and read this question and figure out how to solve it. It says, compute the volume of a solid whose base is bounded by the curves f of x equals x squared and g of x equals 4. So, that's the first thing we're going to do when solving this problem is to draw the base and see what it looks like. Before we do, let's read the rest of the question. The solid has vertical cross sections, and so you're going to do these particular steps when you see something like this, where it says that it has cross sections. Now, the cross sections can vary, so we're going to try to do several examples. And this one in particular, the cross sections are made of equilateral triangles, and we know equilateral means all the sides of the triangle are equal. This last part is equally important, so make sure you highlight this. These equilateral triangles are parallel to the y-axis, okay? So without further ado, let's take a look and see how to solve this problem. With any shape, you want to figure out what its base looks like first, right? So it says the base is bounded by these curves f of x equals x squared and g of x equals 4. So I will say a large part of solving these problems is definitely visualizing what you're trying to solve for. So for step one, we're just going to draw the Cartesian plane, because the base of all of these objects for this lesson, cross-sectional, is going to be on the Cartesian plane. Step two is going to be to draw a bird's eye view of the three-dimensional shape on the plane. So basically what you're doing is you're looking down from the top of the solid all the way through it to the bottom or the base of the solid itself. So we are going to sketch these two graphs, f of x equals x squared and g of x equals 4. Now, you can see that they're going to cross whenever they equal each other, when x squared equals 4. So they're going to cross at 2 and negative 2. So this one's not really too hard to sketch. I'm going to sketch f of x first. And it's going to go up like this on the left. And I don't want to make a V here. Try this one more time. And it's going to go like that on the right. It's not perfect, but it's pretty close. And then g of x, which is equal to just 4, is going to go right above it. And you don't have to extend it out further than where it crosses f of x, and that's it. Okay, so this is the base of our solid object. And the cross sections are going to be basically popping out of the screen, if you will. And we're going to take a look at what those look like in just a second. But anyway, here's the base of your object. And so, you could say it's a U with a basically line on top of it. So always draw the base first and then go from there. Step 3, draw the shape of the perpendicular cross sections. The cross sections that are popping out are equilateral triangles. So I'm just going to draw that. Now, it's really hard to draw 3 dimensions on a two-dimensional plane, but basically these triangles are going to be parallel to the y-axis. They're going to be popping up out of this and forming a 3-dimensional shape. And I do have some software I'm going to use to show you what that looks like. Okay, so here is our graph. I'm looking at it at an angle. We have f of x equals x squared with this u, and we have g of x equals 4 right here. Now with the software, what you can do is you can choose what your cross sections are. In this case, I have the equilateral triangles checked off. I have my bounds correct from negative 2 to 2, which is where these graphs equal each other. So now what I'm going to do is first just look at what these cross sections look like. You can see that it changes. The height of this triangle changes because the base changes, and that's because the distance between f of x and g of x changes. Okay, so this is what our cross sections look like. You can see they're parallel to the y-axis. This red down here is the x. Now what I'm going to do is trace these shapes, and then you will be able to see what this more or less what the solid looks like. Okay, so as you trace these different cross sections, you can see that it starts to form a 3-dimensional shape. Okay, and you can rotate this and kind of see what it looks like from every angle. It is a very odd looking shape, kind of like a wedge, I would say, maybe. At any rate, it's 3 dimensions, right? You know, it's got a base with those 2 graphs, and it's got cross sections that are formed by equilateral triangles. So that's going to give you a very good perspective as to what we're trying to find. We're trying to find the volume of that solid. All right, let's move on to step 4. It says sketch the lines of intersection of the 2 cross sections on the Cartesian plane. So basically what you're going to do is you're going to go back and draw your base. You've already drawn it, by the way, and you're just going to see what those cross sections look like in comparison to that base. All right, so here's my base of my shape we were just looking at. And again, you know, when you're solving these problems, you're probably not going to have software to actually visualize it. But what you can do, since you know that the bases of each of those equilateral triangles are parallel to the y-axis, I like to draw some dotted lines to show, and of course one of them is going to be right on top of the y-axis, but draw at least 2 of them. But of course, as they go along, they're going to change length, or the bases are going to change. Notice the first equilateral triangle will be nothing, right? Because it's a point. But these are the bases of these triangles that will, like I said, be basically popping out of your paper, popping out of your screen, as we just visualized. And because they're equilateral, every single length of this triangle that's popping out is going to have the same length. But you know, I would definitely draw these cross sections just so you can kind of get an idea, start to get an idea of what these dimensions are going to look like in terms of x, because that's ultimately what you're going to have to do. So write it in terms of x. Step 5, label the dimensions of the perpendicular cross sections. So there we go. You know, what I like to do is just basically redraw the shape. I'm not perfect, but again, this is an equilateral triangle. So, you know, the question is, first of all, the base. What is its dimensions? Well, as you can see, it's just the top function, which is g of x equals 4, minus the bottom function, which is x squared. So guess what? This is going to be 4 minus x squared. All right? And the same is going to be true for the sides. 4 minus x squared here, and 4 minus x squared here. Now, here's the issue, and I want to make this a little bit thinner. It's a little bit too thick. The issue is, how do you find the area of a triangle? Well, you have to know its height, right? So we need to know the height of that triangle in terms of x, right? So the thing is, you know, to solve for this, we're going to have to use the Pythagorean theorem. We can see that this, if we cut the triangle in half like this bottom piece is going to be half of 4 minus x squared. Move this out of the way. Okay, and then we can use the Pythagorean theorem to solve for this height. So give me a second to solve that, and then we will go from there. Alrighty, so we will use the Pythagorean theorem. Again, the length of this little part of the triangle right here is half of the original base. So it'll be 1/2 4 minus x squared plus b squared, which will be our height, is equal to c squared. Just square both of these, that becomes 1/4, and then subtract 1/4 4 minus x squared. Forgot the squared here, from both sides. Now you can see that this is actually 4/4, right? It's the same as, well, 1 is the same as 4/4. So when you subtract 1/4, 4 minus x squared, you're going to get 3/4 of the same thing. So you get b squared, which is your height, is equal to 3/4 4 minus x squared. Take the square root of both sides to cancel the square from the b and from the right side, and then the square root of 3/4 is the square root of 3/2, and the square root goes away. So the height is square root of 3/2, 4 minus x squared, and I'll even write that as height because we need that for the area formula of our cross section. You will always need an area formula for a cross section. When you integrate that on an interval, it gives you volume, which we'll learn here in just a second. So step 6 says to determine the formula for the area of the perpendicular cross sections. So basically the area of this triangle, which is going to be, again, 1/2 base times height. And that's true for every triangle, certainly not just equilateral triangle. So half of the base, again, would just be the 1/2 4 minus x squared. So we'll just put that in there. And then the height that we just figured out is the square root of 3 over 2, 4 minus x squared. Okay, now this can be simplified a little bit, and because of that, I'm just going to go ahead and simplify it. So it's going to be multiplying the 1/2 and the square root of 3 over 2 gives you square root of 3 over 4. And then you have 2 4 minus x squareds. You might as well just write it as 4 minus x squared. Okay, so that will be the area of your cross sections that are made of equilateral triangles. Step 7, determine the limits of integration, the range of the perpendicular cross sections. This is why I sketched it. Okay, so basically these purple things, which is the base of our equilateral triangles, what are their ranges? Well, everybody can see that they're going to range from -2 all the way to 2. So I'll just write that out. It doesn't really take much. You can write it as interval notation. If you want to, you can make sure that you write it in terms of x, so x is within that range. Now, this is important because if your range is in terms of x, then your area formula has to be in terms of x. Unfortunately, it already is. Sometimes it's not, and you have to kind of switch that around. So if this were y, you basically have to go back to the original formula to convert it so that's in terms of x. All right, leads us to step 8, which is to set up your integral. Where volume comes into play. So when you integrate area on an interval, you get volume. And what's your a and b? Well, a and b is nothing more than your range. Okay, so this is your a value, and this is your b value. Your left and right ranges of your cross sections. So when we set up this particular volume formula of our solid, it's going to start at -2. It's going to go to 2, and then we're just going to plug in the area formula for each of those cross sections. Okay, so that's going to be the square root of 3 over 4, 4 minus x squared. Okay, and then don't forget your dx, because that's what you're integrating with respect to. And believe it or not, this formula right here is going to give you the volume of this solid. Now you might be thinking, well, why does this work? We've never used integrals to find volume. Well, let's take a look back at our visual 3D of this shape to get a better understanding of why this formula works. Again, this right here gives you the area of each of those triangles, and we're going from -2 to 2. Okay, so the area of each of these triangles in blue, as we said before, is just square root of 3 over 4 times 4 minus x squared, and we're going from -2 to 2. So just imagine if you have infinitely many cross sections for this three-dimensional shape, right? So let's just start at -2. Obviously that doesn't have any height at all, so there's really nothing there. But as you keep going to the right, as I said, there's infinitely many triangles. Each of those triangles has a particular area, which again is represented by this part of the formula. The thing is, if you integrate that from -2 to 2, meaning you add all of those areas up, you will get the volume of this three-dimensional shape. Now that we can click trace shape, and what I'm going to do is I'm actually just going to go ahead and draw it with the software. You can see all of these individual cross sections have areas, and if we integrate it from -2 to 2, we get the volume of this three-dimensional solid, which is really cool. I love this lesson just because you can generate so many different types of solids, so many different shapes using cross sections and using the integral. So now that's all that's left to do is to actually integrate this formula. Unfortunately, we've got something being squared within in parentheses, a function within a function, and so what we're going to have to do is expand that so that we can integrate it. Now let's read step 9 together because it is important at times. It says determine a relationship between the variable of the integrand and the variable of the limits of integration. So this is what I was going back to. This worked out for us this time because these limits are in terms of x, which is the same as what this is in terms of. If that were not the case, for example, if these limits were in terms of y and this was x or vice versa, you would have to make sure that they were both that way. So basically, step 9 is already done for us for this example. We'll take a look at another one where that's not the case and we'll have to change it. Step 10 is basically the same as step 9. If that were the case, you would use the relationship to write the variable of the integrand in terms of the variable of the limits of integration. In other words, they either both have to be x or they both have to be y. Now we're going to just do step 11, which is to determine the definite integral. So again, we can't integrate this unless we expand this binomial, which is what I'm going to do right now. Okay, so the first thing I did was just pull out the square root of 3 over 4 in front of the integral, and then just expanded this binomial. It's going to give us 16 minus 8x squared plus x to the 4th. So now we can actually integrate it, without having to do any kind of special integration method. So I'm going to go ahead and do that right now. Okay, so again, I'm just leaving the square root of 3 over 4 out of it. The antiderivative of 16 is 16x. Antiderivative of 8x squared is 8x cubed over 3. Don't forget minus. And the antiderivative of x to the 4th is 1/5 x to the 5th. Here are my limits of integration. So all I have to do now is plug these in. And again, that will give you the volume of the solid that we've generated. Okay, so I'm not going to spend too much time on the number crunching here, but basically going to plug in 2 for your upper limit into your antiderivative equation, and they're going to plug in -2. Always make sure when you're subtracting your lower limit you put it in brackets. You're going to end up with some fractions, and you're going to combine those. Make sure you distribute your negative correctly. The common denominator here is 15, so you have to find a common denominator, combine the numerators, and then 512 over 4 is 128, which leads us to our final answer of the volume of the solid is equal to 128 times the square root of 3 over 15, which is about as accurate as we can get. Now, what is that as a decimal? Well, let's pull up the software and see what we get. All right, so let's go ahead and draw our solid one more time. Here's our cross sections, that equilateral triangles that go across our graph that's bounded by g of x equals 4 and f of x equals x squared. And we see that we get a volume of 14.78 for our solid that has cross sections equilateral triangle bounded by these two curves. That's it for this lesson. I think the key is finding your limits, figuring out what your upper and lower bounds are, which will determine the dimensions of your shape, depending on what the cross sections are. It could be semicircles, triangles, rectangles, squares, whatever. Visualizing is very important, and also precision and making sure that you're very clear about every single step, going back and make sure you did it correctly, your minus signs and all that kind of thing. So if you have any other questions about finding the volume of a solid with known cross sections, let me know.